Welcome to Chapter 10, Thermodynamics. We're going to talk about Section 1 still. This is Part B, and we are going to talk about thermodynamic processes. So this time we are going to distinguish between isovolumetric, isothermal, and adiabatic thermodynamic processes. So let's look at what a dynamic process is first. So work, heat, and internal energy are all part of thermodynamic processes. They are all always present in one way or another. And often both work and heat are how energy is transferred within the system. Rarely is it only one or only the other. So it will rarely be just work. It will rarely be just heat. Often there's a bit of both going on that are moving in the system. So many processes, though, even though both are present, often will get heat or work that is dominant, which means that's the one we have the most of. And so we can approximate it or pretend to make it easier for ourselves that just heat or just work is being done. And it's often close enough that it helps us solve real-life systems, even though both are present. So today we're going to look at several examples that are called ideal examples because they're ideal where it would only be either heat or work that is happening, okay? And we're going to only talk about it involving gases because it's easier to study the process and understand what's happening on when we talk about gases. So the three ideal thermodynamic processes are isovolumetric, isothermal, and adiabatic. And I just want to pause here to help you remember these words for a little bit later, and let's kind of take a moment to see if we can see anything that we recognize. So these first two words have the prefix iso, okay? And maybe you know the word isolate. Okay, isolate means to put something off by itself, so it's separated from other things. Okay, and that kind of means the same thing here. You can kind of think of it as saying only. Okay, iso, and then we have this word volume in the middle, volumetric. Okay, so this one we might have to do, having to do with only volume. Okay, isothermal then, you might remember from the last video, thermal has to do with temperature and heat, right? So we're going to have something that's only about temperature. And adiabatic is a little bit trickier, and we won't go into adiabatic then. So just make sure you focus on understanding and remembering these two, and that will help you remember this one. Actually mean now. So our first one is isovolumetric. And the only thing about this, because remember I said iso kind of means only or separate, is that it's constant volume. So volume here is the key, and it's constant. Okay, that's how it's separated from the other things. It's the one thing that's not changing. So when volume doesn't change, if you remember, we had the equation where work equals pressure times the change in volume. So if volume doesn't change, if this is 0, then work is also 0. Okay, so no work is done on or by this system. And an example of how this happens is we've talked about calorimeters before. And so here is a picture of what is called a bomb calorimeter. And the reason it's called a bomb is because it can hold a lot of things and a lot of pressure inside of it without changing its shape. So this is a very solid structure. It won't change volume. It's a solid metal. And so we're able to do calorimetry experiments without worrying about any of the energy going into work by changing the volume of a system. The next kind is isothermal. So isothermal is a little trickier now to explain and understand. So in isothermal, because thermal means temperature, that means our internal energy, U, is constant. So there's no temperature change. Okay, so we could also say here delta T is going to be also equal to 0 along with delta U. Those are both 0. So what that means is if there's any changes going on, our heat added or lost by the system must be equal to the work done on or by the system. So these kinds of processes will always happen very slowly, and that slow process is what allows it to stay at a constant temperature. So the example that your text gives is a balloon slowly being inflated, and so that as it expands, the work it does on the surrounding air is equal to the heat added back to the balloon by the air. So what that means is as our balloon, if it were to get a little bit bigger, an example in your book talks about it being inflated by pressure. Okay, so it's inside a building, but the weather changes, so the pressure changes, and that allows the balloon to expand. Maybe you've noticed sometimes that if you take a balloon home and then it gets cold, it shrinks. Okay, well, if it heats up, it'll expand. Okay, and that works for pressure too, not just heat. So this case, it's pressure, not temperature. So as the temperature decreases, the balloon expands, but it's doing it very, very slowly. Remember, as the balloon expands, it's doing work on all the little air particles that are out here because it's moving them. It's a force that's causing a change in displacement. And so as it moves those particles, they actually heat up a little bit. And if this is done slowly enough, then that temperature is added back to the balloon so that the heat lost here will, or excuse me, the work done here will equal the heat added back to the balloon. So it's kind of a cycle, okay? So you do a little work, okay, that goes out, that work heats up the surroundings, okay, and then that temperature is added back into the balloon. And so you end up with this cycle where Q always equals W, and so there's never a change in temperature. So I'm going to show you another example now of isothermal that's maybe a little easier to understand than this one. This one is our ideal example. The next one I'm showing you is not ideal, okay, because this one we have something called a closed system, meaning no energy is going in or out. The next example is not a closed system, and it involves water and gas. So our next example is not. So again, this is our not ideal example, but it will help you understand the idea of what isothermal means. So what we have here is we have a liquid changing to a gas. And if you remember from the last chapter, that always happens at a temperature. So if this is water, okay, if this is water, then this is all happening at 100 degrees Celsius, right? But when water becomes a gas, okay, so here it's a liquid, and here it's a gas. Okay, as that happens, it expands. Okay, and because it's expanding, it does work. So the heat added will equal the work done to change the volume because we know the temperature won't change. We know it stays at this 100 degrees. So you could think of this too as another place that all that energy goes in if you still were struggling with that concept of where all that heat goes when you have a change in phase. Well, it's going to do work to expand the molecules of the water. Okay, so this is isothermal, okay, because the temperature does not change. So our last one then is adiabatic. Okay, so adiabatic is when we have no energy transfer as heat. So our Q equals 0 this time. Okay, in order for this to happen, unlike isothermal, this needs to happen rapidly or very quickly. Okay, so a gas needs to expand quickly, and it needs to be insulated from its surroundings so that Q can't cross the barrier. So a good example of this would just be if we had some gas here and some volume, okay, and it's all hanging out there and it's at a higher temperature. Okay, so right now its temperature is a higher temperature right now. Okay, and then if you suddenly released this valve here in the middle and let it go, then they would suddenly expand to fill this space. And right now there's nothing in here. This is a vacuum. So there's no matter in there for it to mix with. Okay, when it does that, if there's no way for heat to enter or exit it, okay, so heat can't come inside, it can't go out, then all of a sudden all these particles that were moving so fast, they've got more space to move, and so they're actually going to slow down. And because they're slowing down, remember temperature is proportional to the average kinetic energy. So as the particles slow down, then the temperature has decreased. So this is one way to change the temperature of something without using heat. Okay, so you just have to suddenly expand a gas. Okay, or you could do the opposite to increase it and suddenly decrease the volume, and that would increase its temperature, or increase the volume and that decreases the temperature. So this is called adiabatic because even though the temperature, or as we talk about it in here, the change in internal energy, okay, so this will change. Okay, work happens, right, because we've got this moving. So we've got work and internal energy, but Q is 0. So heat is not how we change the temperature. So just to summarize here, I made this little table for you, okay? So we learned about isovolumetric. There's no work done because there's no change in volume, so W equals 0. And because of that, our change in internal energy will equal our heat. Okay? Isothermal, there's no change in temperature or internal energy. Okay, so delta U is 0. So our heat will equal our work, and it must happen slowly. And then the last one is adiabatic. There's no heat, so Q equals 0. It needs to happen quickly, and the work will equal to the change in internal energy. So even though there's no heat, temperature does change. All right, so that is the end of Chapter 10, Section 1. Let me know if you have any questions, and I'll see you guys later.